Well, acids and bases. An acid is a substance that donates a proton a hydrogen ion or hydronium when dissolved in water. Now, there are two definitions of an acid, one by Arrhenius and the other one by Brosted and Lowry. Arrhenius says an acid is a substance that produces hydrogen ions when dissolved in water. Now be careful, Arrhenius make mention of water, while Lowry and Brosted don't make mention of water. Now a base is a substance that accepts a proton. A base acid is a substance that, and a base accepts a proton. Now, we have to look at properties of acids. They have a pH which is less than 7. Gastric juice in the stomach, gastric acid. The lemon, pH is about 2 there, 2.5. Grapes, tomato, those are examples of an acid. And then examples of a base, ammonia, which you always use in handy there for cleaning purposes. Egg, your soap, your baking soda. We also have water. Water has a pH of 7, so water is neutral. Water is neutral at pH 7. Now, let's look at this reaction here. If you have A plus B, that will give you B. If this is an acid, for the fact that it can donate a proton, it becomes an acid. And then you have that plus A, or you can also have HA plus a B that is potential to can accept a proton. That becomes BH plus A. Let's look at simple one like hydrochloric acid. Base, strong one, potassium hydroxide. That will give you water plus a salt. Now, I hope you appreciate that this substance here has a potential to donate a proton. Therefore, by definition, is an acid. This one comes the base. Now, this one just become a spectator ion. It's not taking part there. Let's take another kind of an acid. This time we are taking on a weak acid. Plus your ammonia there. That gives you the ammonium ion there. What do you have? That is a proton transfer. Now let's see what has been transferred here. By the very definition of an acid, this person has been transferred here. We have H, 3 H's there, plus that one which goes up there, makes up 4 H's. Therefore, that proton has been transferred. Now, let's have a look at, I said this one is a weak acid. And I said that one is a strong acid. What the difference? This one here is a strong acid because it's eager to donate a proton. It will dissociate completely. This one is not eager to donate the proton. That's why it's a weak acid. Now, let's have a look at an acid reacting with water. What you call an aqueous solution. You have water there, which has got the proton added, which was donated from an acid. Let's see here. This is aqueous here. Aqueous. Now so let's have a look at sulfuric acid. That's sulfuric acid reacting with water. And that gives you your hydronium ion. And the sulfate ion there. This is exactly how Arrhenius view this. Because water here accepted a proton from this side. Water here accepted the proton to there, so that it gives us the hydronium ion there. Water qualifies to be called a base because a base accepts a proton. Now we can also look at a base reacting with water. Let's look at ammonia there. By the way, you can balance that equation. If it's balanced, I think we need to put a 2 here. You can also put a 2 there. 2 H's here. 3 H's there times 2 is 6. I have 2 here. I have 4 plus 2 is 6. 3 times 2 is 6. So if I have ammonia plus water, water is always a liquid there. You get an H4 because hydrogen moves from here, goes down, and then you have an OH, aqueous solution. What do we have? So let's have a look at sodium hydroxide. In water, you get an OH there. Aqueous there. Now be careful. Sodium hydroxide dissolves in water, and the proton transfer does not occur, which is called proteolysis, does not occur. Be warned. Now, as I said, that the donation of a proton on an acid can be a characteristic property of an acid, of course. Now, you should be very careful. You don't pour an acid into water because that's too dangerous. The temperature will go up quickly and that might explode. You always pour an water to an acid. No. When an acid dissolves in water, a chemical reaction takes place, and that is marked by a rise in temperature. So you don't pour an acid into water, pour water into an acid. Now, an acid, there's what you call a pH scale, which starts from 1 to 14 there. Here we have 7. Here, acids. Here are alkalines. Here are the bases. That's where you find ammonia. That's where you find your grapes, your lemons. pH is low there. Now, a strong base, in as much as on the previous page, we talked about a strong acid. We can also talk about a strong base. A strong base here. Sodium hydroxide, potassium hydroxide. When a strong base dissociates in water to form the ions, like I've shown you on the previous page here, where we had in here on this one here, this is strong base dissociating water to form a sodium ion and an OH ion there. This one is a positive ion, which is called the cation, a negative ion, which is called an ion. And this is called ionization because ions are formed this reaction here is called ionization because ions are formed there. Now, pH here is the negative logarithm of the concentration of a proton there, while a POH is equal to the negative log. This square bracket stands for concentration. That square bracket stands for concentration. That's what you do. And these are logarithms to base 10 here. So if you have the concentration of a substance, you can get its pH value. If you have the pH, you can also give the concentration. Now, we also have what you call conjugate acid-base pair. Conjugate. Conjugate acid base pair. Example, if you have an acid and a base, that will give you a conjugate acid and a conjugate base. Yeah, can call that acid there and base there. And then you have a conjugate acid and a conjugate base. What we have. You can have, for example, ammonia, NH3, and H3 plus a proton there. That gives you the ammonium ion there. By definition, this has accepted the proton there. Therefore, this one will be our base and We have our proton there, and then this one will be our conjugate. Conjugate acid. Why? Because this is able to donate a proton and becomes that. So because it can give a proton, it becomes an acid by definition. What do we have? Now let's have a look at hydrochloric acid and ammonia. Hydrochloric acid and ammonia, which will give us the ammonium ion plus. Now this, you know, is an acid. That is our base. And then this one becomes, our acid. And then that one becomes the base, because this can accept the proton to give us a hydrochloric acid there. Therefore, acid and then here we have a base to an acid. Here we have an acid to a base. These are conjugate pairs. These are conjugate pairs. Let's have a look at acetic acid. The one you get in a vinegar. And sodium hydroxide. Let's see what happens there. Plus H2O. Now, we expect to have sodium ions plus them. Now, this will be an acid. That will be a base. That will be a base. That will be an acid. Now, from acid to a base, a base to an acid there. These are conjugate pairs. These are conjugate ace-base pairs. Now, let's have a look at kinds of acids. I said hydrochloric acid, sulfuric acid, nitric acid. These are strong acids because they are eager to give a proton or dissociate completely. Now, then we have acetic acid there, which is of course a weak acid. Now, we also have to understand dilute acid and concentrated acid. The same can apply for base. By concentration, if we say is concentrated acid, it has more number of moles per given volume. And if it's diluted, it has less number of moles per given volume. Now, basically, you can have 1 liter of water and you can pour or measure. You can measure 4 grams of sodium hydroxide. Or you can measure 16 grams. Now you can convert, you know, that number of moles is equal to the given mass. Given mass divided by the molar mass. So the molar mass is there will be 23 plus 16 plus 1, that must be 40. So we have 4 divided by 40 grams per mole. So grams here. Gram will cancel the gram, remember with moles, 0.1. 0.1 divided by 1 decimeter cubed. That will be the concentration of this sodium hydroxide. But if you pour 16 grams of sodium hydroxide into 1 liter, this is the concentration here will be far better than the concentration there. Now, we can have a dilute acid, or we can have a strong acid which is diluted. We can have a strong acid which is diluted, or we can have a weak acid which is diluted, or a weak acid which is highly concentrated. That's possible. Don't mix the two. Don't mix the two. Now, if we look at I've given you a hydrochloric acid here, sulfuric acid there. Let's have a look at what happens here. Hydrochloric acid can only give 1 proton. It's mono. So that is called monoprotic acid. Mono for 1. And then we can have sulfuric acid. Which can give us 2 protons. And then this is diprotic. Diprotic acid. Now, we can also go to triprotic acid, H here, and then this is triprotic. This can give 3 protons. Now, I want us to have a look at what actually happens here at molecular level. I want us to have a look at what actually happens here. Here is that we can have H2SO4. That will give us a proton, SO4 minus. Now, this one here, on its own, this HSO4 can give you now. I hope you realize that the first proton is there, the second proton is there, those two. So because di for 2 diprotic acid. That's how it goes. Now, we also have substances that can either be an acid or a base. They act like an acid and as a base as well. They are versatile. Example, let's take water. Let's take first hydrochloric acid. I think we have met this reaction before, plus water. That gives you hydronium ion plus chlorine there. And let's have a look at ammonia. With water there, give us the ammonium ion, OH minus. Now this one here is an acid. This one here is a base, which makes this one an acid. This is an acid, which makes this one a base. Now you can see that water can be a base and water can also be an acid. And therefore we say it's an ampholyte. Acts as both an acid and a base. That's an ampholyte, a substance that can react as a base or as an acid. Now, we are going to have a look at the reactions of acids and bases. that will be later on. But for now, we can have a look at titration. Now let's end up here. The next lesson we'll go to titrations, whereby an acid neutralizes a base or a base neutralizes an acid. But before we go to titrations, we need to define a standard solution. A standard solution is a solution of known concentration. Standard solution is a solution of known concentration. On the previous page, I said, if you measure exactly 4 grams on a scale, precisely 4 grams on a scale, you actually have 0.1 mole of sodium hydroxide. It's easy for you to measure 1 liter, 1000 cc. Now, if you have that kind of moles per, this will become a standard solution because the concentration here is known. Now, if you look at these equations here, see which one, of course. This one here, whereby we have an acid there and we have a base. Now, 1 mole of an acid requires 2 moles of a base. For progress, let's say you have sodium hydroxide react with hydrochloric acid, and that gives sodium chloride plus water. And then you have sodium hydroxide or potassium hydroxide reacting with sulfuric acid. You have sodium sulfate plus water. Let's look at there. You have 1 sodium there, 1 taurine, 2 H's, 1 O. That one is balanced, naturally balanced, God given. Here we have Na, which is 1. I have 2 there. It means I must put it. If I have to balance that, I must put a 2 here. Therefore, here 1 mole needs 1 mole. Here 2 mole needs 1 mole to give us 1 mole and 2 moles of water molecules. Now, concentration is number of mole per volume. Therefore, number of moles here so if I multiply concentration by volume, I'll get number of moles. Now with reaction A, titration B there, on B there, I hope you'll appreciate that with A, I'll have 1 mole of a base, which is equal to 1 mole of an acid. But here, that goes for reaction A. What happens at B there is that I have 2 moles of a base reacting with 1 mole of an acid. If you go back to our measurement there, we shall be knowing the concentration of sodium hydroxide, which means we know the concentration of a base, the volume that can be measured from the burette or the pipette, from the flask, Elmer flask, and then we can get the concentration of this unknown acid. The volume, this will be basically from the burette, that will be measured from the pipette in this kind of an arrangement. We will have a look at the second lecture where we will have a look at titration on its own and look at some calculations and questions and understanding what is the endpoint, what is an indicator. Otherwise, for now, that will be okay. Till we meet next time. Hope you enjoyed.